Hi, my name is Amy Fan, and I decided to do my project on a Kaggle competition data set. This one is the Jane Street stock market data, so I'm trying to predict stock data over time. So some overview is that I'll start off with explaining what the data is structured like. I will explain my model of choice, and I will go over how I ran the model, how I cleaned the data, the results, and some final notes. So in terms of the data set format, it has around 10 million rows of data and 92 columns. These 92 columns roughly fall into 5 categories. Two of them are called date ID and time ID. These are time-based columns and variables. So I just decided to combine them into a single time column since they go together very well. And then another column is the symbol ID column. So this is a unique financial instrument such as Apple or Google or VU, some kind of stock that you're interested in. These are actually anonymized, so it's like 0 through 38, and there are some more as well. So basically it stands for the type of stock ticker symbol, but it's anonymized as integers. And then weight is another column, and this is just used for evaluating their scoring function. And then 79 of the columns are features, and these are anonymized market data, and 9 of them are responders, which aren't really explained, but you are interested in predicting responder 6 over time. And this is for multiple symbols, so you're interested kind of in the symbol responder 6 pair. So I decided on a model called a long short-term memory model, which is shown up here. It's also called an LSTM, and it's a specific type of recurrent neural network that works for sequential data. And you can see this, I got this from a website where basically you have something called a memory state and a hidden state. So most RNNs will have this, and it learns sequentially over time. But the special thing about LSTMs is that they have this long-term memory using a skip connection that allows you to prevent the issue of decaying gradients, which is an issue because you're trying to learn over time, and sometimes as you learn, you kind of forget information. And the information you learned before gets less and less relevant, and it gets less and less influence from new learning and new model training. So RNNs are also known for recurrently predicting, so which is perfect for my data set because I want to take my output and predict the next inputs in a way that allows me to predict a long sequence. So I'll go into the data cleaning step. The first thing that I did was shrinking the data set because I am not using a GPU and I'm currently using a CPU, so I don't have as much computational power for this project. I'll eventually use a GPU on a later step, but not right now. So for now, I've subsetted the rows from 10 million to 1 million rows, and I have subsetted the columns, also known as variables, for learning, from 92 to 14 columns. And these columns that I picked were time, because this is sequential data, symbol ID, and responder 6, because these are the important responses that they care about, weight, because it's just seemed interesting, so I manually kept this one, whether or not it's actually useful. I just thought I would include it. And then top 10 features, out of the 79 features that were in the original data set, I kept the top 10 that I had found the highest correlation with responder 6. The second step that I did is reformatting the data set. So for the LSTM model, it likes a particular format, and I just kind of went through and cleaned that out. Since we're interested in responder 6 over time for every symbol, I decided to subset the data frame into multiple tensors for each symbol. So basically, for each symbol, I would take out slices of the data frame that only had that symbol. So I would basically have, if I had 38 unique symbols, I would have basically 38 tensors. I reformatted it into tensors because I can change the shape into something that I like, and then it's laid out into a time sequence. So dimensions for each tensor are 1 million because there are a million rows, and then 12 because that is the number of interesting variables that I care about. So the reason why it's 12 is because the symbol and time columns are inherited by the reformatting. And then for each symbol, I'm training the model on a hyperparameter, so this is 100. So a 100-day sequence of data, so the length of my input is 100. I put an 100 length input into the model each time that I train it. So this is just a hyperparameter. And then after that, I compute the loss and I allow the model to improve through backpropagation and a stochastic gradient descent-like algorithm, which is something we talked about. And the one that I used is very similar to stochastic gradient descent, and it's called ATOM, which is basically the same thing. It works very similarly, but it just allows the learning rate to change instead of being a fixed value. So it'll have an adaptive learning rate. And then I computed the test loss every 900 epochs. I'll have the results in the next slide. So you can see here that the for all of these symbols, you can see how the training improved. And I'll go back to explain a little more. So importantly, for each symbol, I would train the model. So I trained on, in the next slide, you can see I trained on all of these. So I trained sequentially in the sense that it's sequential data, but also I trained it symbol by symbol. So I would train on the entire, or I would train on symbol 0 first, and then I would train on symbol 1, symbol 2, all the way down to symbol 38. And this allows the model to generalize and learn how to predict new symbols that aren't in this data set. So here you can see that these few symbols, I think these 5 are one of the earlier ones. So you can see the pink one is up here, symbol 1, 0 is symbol 0. So these are the ones that are driving most of the initial learning and allowing for some generalization. And then you can also see some other differences in symbols that are less easy to understand. You can also see the loss over here. You can see that similarly, there are some that do very well and some that do somewhat poorly because they don't generalize as well. And I'll explain some of them in the final notes. So you can see that the model begins to learn sufficiently at around 900 epochs. It'll either kind of decide that it can or can't learn something at that point. So you can see in the train around 900 epochs, things start tapering out mostly. They don't really improve too much, as well as here in the test. You can also see the test loss is generally lower than the train loss, and this is mostly because of the way I calculated it. So the way I calculated train loss is, so I batched the data and I computed the train loss on only a single batch for every epoch, so it's more stochastic, versus the test loss I computed over the entire data set, the entire testing data set, which is a lot larger than one batch in the train loss. So this makes sense, but they're roughly, they mimic each other's behavior. And then the model generalizes well for most symbols except symbols 14 and 13, so we can go back and see in the train data set 13 and 14, or I guess it's, let's see, so 13 and 14, it's these two for the test data set, so it's learning in the train data set and it's not doing very well at predicting for symbol 13 and 14, which suggests that they're less similar to the other symbols and harder to generalize and understand toward. And then the final note is I ran this using PyTorch, and it's also doable in Keras, or in R using the Keras package for LSTMs, but Python was faster for me, so this is what I stuck with. I wasn't actually able to complete many epochs with R, so that's something that I had to consider and switch.